Welcome to the deep dive. Today we're venturing into this really fascinating idea of galactic shepherds.
Right.
Basically, how these truly massive objects use gravity, just pure gravity, to act as sort of unseen architects.
Shaping the structure of entire galaxies, yeah.
Exactly. We're drawing on a discussion from the Sci-Blowing show, specifically their piece, Galactic Shepherds, Shaping Stars with Gravity.
It's a great source for this.
Our goal really is to look past the idea of the cosmos being just random
Uh-huh.
and instead try to uncover this, well, gravitational choreography that's constantly playing out.
Understanding the invisible forces sculpting everything we see out there.
Precisely. Getting a deeper feel for how these galactic landscapes get formed. So let's kick things off with the main player, gravity itself.
Indeed. And as the Sci-Blowing material points out, gravity totally dominates on cosmic scales.
Which is wild considering it's the weakest fundamental force, right?
It is. It's quite something. But this subtle pull, it's what binds stars into galaxies in the first place.
And shapes things like spiral arms.
Spiral arms, our own solar system, even black holes. It all comes down to gravity.
And a key thing to remember, unlike, say, electromagnetism.
Which can push and pull.
Right. Gravity only pulls. It's purely attractive.
Always attractive, yeah. But its reach over these vast distances and timescales is just immense.
The Sci-Blowing host called it the great artist of the universe. I like that analogy.
It fits, doesn't it? Sculpting these incredible celestial views, thinking about space-time itself like Sean and Carroll explores.
From eternity to here.
Yeah, that really drives home how fundamental gravity is to forming these big structures.
Okay, so to get a handle on how this galactic shaping works, maybe we start smaller.
That's a good idea. The
Right.
Sci-Blowing episode used the example of shepherd moons.
Like Prometheus and Pandora around Saturn.
Exactly, within Saturn's rings. It's really interesting how these relatively small moons use their gravity.
To sort of corral the ring particles.
Yeah, exactly. They can find the particles, they clear out gaps, keep those sharp edges we see.
Like tiny little cosmic sheepdogs for ice particles.
That's a good way to put it.
So the obvious question then, which the source also brought up, is if these little moons can do that locally, could something similar happen on a much, much bigger scale?
With stars, you mean?
Yeah, stars within whole galaxies. Could gravity herd them too?
And the answer, according to the source, seems to be yes.
Yeah. Okay.
The Cassini images, the ones from that 2005 Science article, they gave us stunning proof of how effective these moons are with Saturn's rings. Gravitational shaping in action.
Right. So let's scale up to galaxies like ours, the Milky Way.
Okay, so now we're talking about how gravity organizes the really big structures in spiral galaxies.
And gravitational resonances come into play here.
That's a key concept. Think of it like pushing a swing. Right.
Timing it just right.
Exactly. You match the natural rhythm and the swing goes higher. In a galaxy, certain orbits and speeds can kind of reinforce each other through gravity.
Leading to things like galactic bars, those elongated cores.
Precisely. And those bars, they're important because they actually redistribute angular momentum.
The galaxy spin, basically.
Yeah, they mix things up in terms of spin.
And then the spiral arms, the really iconic feature.
Right. Now, what's fascinating, and the source highlights this, is that the arms aren't fixed structures made of the same stars moving together.
Okay, so not like solid arms rotating.
No, more like density waves. Think of them as regions where stars and gas temporarily slow down and bunch up.
Ah, like a cosmic traffic jam.
That's the perfect analogy. The stars and gas flow through the arm pattern, slowing down in the dense part, which triggers star formation, and then moving on.
And we can't forget the dark matter halos.
Absolutely not. These huge, invisible structures surrounding galaxies, they're the dominant gravitational influence.
Affecting star formation rates, rotation speeds, everything.
Pretty much everything within the galaxy, yeah.
So the combined gravity of these bars, arms, dark matter, it has real consequences.
Oh, definitely. It can trigger massive bursts of star formation when gas gets compressed. It can nudge stars onto completely different orbits over millions or billions of years.
Wow.
And it can even funnel gas and stars towards the supermassive black hole at the center.
Feeding the beast, so to speak.
Essentially, yes. Fueling its activity. The Sci-Blowing host put it nicely. It's not chaos, it's curated.
Curated, I like that.
Yeah.
So gravity is actively managing the galaxy.
That's the picture that emerges. There's a lot of complex physics involved, detailed in papers like that 2014 Astrophysical Journal article on spiral dynamics.
Okay, so that covers the internal sculptors. But the Sci-Blowing show also talk about external influences, right? Other galactic shepherds.
Yes, exactly. Things outside the main galaxy that can still exert gravitational influence.
Like what sort of things?
Well, first off, dwarf galaxies and satellite galaxies.
The smaller galaxies orbiting bigger ones like ours.
Right. As they orbit, their gravity pulls on the larger galaxy. It's a constant, gentle tugging.
But over billions of years.
It adds up, it can create ripples and pull out long streams of stars into the halo, like tidal effects, basically.
Okay, so interacting galaxies, what else?
Then there are the more, let's say, speculative candidates. Rogue black holes, for instance.
Ones just wandering through space?
Potentially. Or maybe compact clusters of dark matter. We don't see them directly.
But their gravity could still affect things.
Over very long timescales, yeah. They might subtly change star paths, maybe disrupt star clusters. It's less certain, but possible.
And the source mentioned dark matter subhalos.
Ah, yes. Our models of cosmology predict that the big dark matter halo around a galaxy isn't smooth. It should have smaller clumps within its subhalos.
Okay.
And these unseen clumps could be gravitationally hurting stars without us even detecting the subhalos themselves.
How would we know they're there, then?
We'd look for the effects, things like tidal tails, stars pulled out of clusters, or dwarf galaxies, or maybe faint patterns like ghost patterns in how stars are distributed.
It's like cosmic archaeology, trying to find the unseen forces by their effects.
Very much so. The Sci-Blowing quote was great here. We may be surrounded by unseen shepherds guiding the galaxy like ancient farmers of the sky.
That's a powerful image. Okay, this is all fascinating, but maybe a bit abstract. Let's bring it home. What about our own Milky Way? Do we see this happening here?
Absolutely. And this is where missions like the Gaia Space Observatory have been game changers.
Gaia is the one mapping billions of stars' positions and movements with incredible precision, right?
Exactly. And the data coming back is just packed with evidence for this kind of gravitational shepherding right here.
Oh, like what specifically? What's Gaia showing us?
Well, one of the clearest signs is stellar streams.
Those long trails of stars.
Yes, incredibly long, thin streams stretching across vast parts of the sky. Gaia has mapped out dozens of them.
And these are?
These are leftovers. The shredded remains of dwarf galaxies or globular clusters that got too close to the Milky Way and were torn apart by its gravity.
Wow. You can literally see the tidal disruption.
You can. Then there are these vertical ripples, or waves, discovered in the galactic disk, like tossing a stone in a pond.
What causes those?
A leading idea is that the Sagittarius dwarf galaxy, one of our satellites, actually punched through the Milky Way's disk sometime in the past.
And that impact sent ripples out.
The gravitational disturbance could have caused these waves, yeah.
Okay, what else?
We're also seeing strong evidence for stellar migration.
Stars moving far from where they were born.
Exactly. Stars born in the inner galaxy moving outwards, or outer stars moving inwards. This can be driven by those resonances with the bar or spiral arms, or by the gravitational echoes of past collisions and mergers.
So taking all that together, the streams, the ripples, the migration, it's all pointing towards our galaxy being actively shaped by these gravitational forces.
It paints a very dynamic picture, yes. It shows this gravitational shepherding isn't just a theory. It's happening right now in our own backyard. That 2020 review by Amina Helmi pulls a lot of this evidence together beautifully.
Okay, so understanding these shepherds is clearly important for astronomers. But why should we, living on a planet in this galaxy, care about these invisible cosmic herders? What's the bigger picture?
Well, first, it's fundamental to understanding how galaxies like ours even formed.
Reconstructing the history?
Exactly. By studying these streams and disturbances, understanding dark matter's role, we can piece together the assembly history of the Milky Way and other galaxies over billions of years.
Makes sense.
It's also a crucial tool for probing dark matter itself.
Because we can't see it directly.
Right, but we can see how its gravity, including these potential subhalos, influences the stars and gas we can see. It helps us map out where this mysterious stuff is.
Okay, so understanding the past, mapping dark matter. What about the future?
Understanding these forces helps us predict how galaxies will evolve, how they'll continue to interact, merge, change shape over cosmic time.
And does it affect us or life?
Well, potentially, yes. These gravitational shepherds influence where stars form, where they move to, and maybe even what they encounter along the way, like nearby supernovae or dense gas clouds.
So where life might arise could be influenced by this?
It's plausible. The distribution of stars, and therefore potential planetary systems, isn't random. It's guided. It's even possible our own solar system hasn't stayed put its whole life.
We might have migrated within the galaxy?
We might have, yeah. Pushed or pulled by these same large-scale gravitational effects over billions of years.
So the big takeaway seems to be shifting from a view of galaxies as just random collections of stars,
Right.
to seeing them as these incredibly structured systems actively managed and sculpted by gravity.
Precisely. Guided by these gravitational shepherds.
Okay, so as we wrap up this deep dive, maybe the final thought is this. Consider that the beautiful, grand structures we see, spiral galaxies, ellipticals, they might not just be chance arrangements. They could be the ongoing work of these unseen gravitational forces.
It really makes you think, doesn't it? About massive black holes, the whole dark matter scaffold, the gentle pull of cosmic tides.
All working together.
Like a kind of cosmic symphony, orchestrating the structure of the universe.
And maybe, just maybe, figuring out this cosmic choreography, this herding, could it eventually give us clues, a sort of roadmap, to where life might be more likely to emerge?
That's a really profound thought to ponder. And maybe for you listening, exploring some of the public data from missions like Gaia, it could give you a glimpse into these incredible, subtle forces shaping our own corner of the cosmos.